Welcome all to SST College of Arts and Commerce. This is SST Edupedia. Myself, Assistant Professor Yogesh Patil from the Department of Information Technology and Computer Science. Today we are going to discuss the topic Bandwidth Utilization Multiplexing, and this is the topic for SYBSc, SEM 3 for Information Technology and SEM 4 for Computer Science, and the subject is Computer Networks. Let's start with, before starting we have to understand what is mean by bandwidth utilization. Bandwidth utilization is the wise use of availability of bandwidth to activate or to achieve the specific goal. A goal is nothing but like sending or receiving the data, and whatever the data we have sent, whether it is received properly or not from the particular channel. So efficiency can be achieved by multiplexing, that is sharing of bandwidth between the multiple users. So many of times we can see that we are sending or receiving the data through a common data transmission wire, whether it is wired or wireless. So these data transmission channels are shared by these kind of transmission system. So the concept of multiplexing rises over here. So what is multiplexing? Multiplexing, whenever the bandwidth of a medium linking two devices are greater than the bandwidth needs two devices, the link can be shared. Now, multiplexing is the set of technique that allows simulation or a transmission of the multiple signals across the signal data or a single data link. Now, as data and telecommunication use increases, so it causes to the data traffic, and to avoid these kind of data traffics we use a technique which is known as an multiplexing. And in this session we are going to discuss the different type of multiplexing, that is frequency multiplexing, wavelength multiplexing, synchronous, that is time division multiplexing, and statistical time division multiplexing. So let's understand the concept of multiplexing. When a common channel, that is we have one link and n number of channels over here, n number of channels in the sense there are n number of senders as well as n number of receivers. So the multiplexer at the sender end multiplex the data and it transferred that data through a one common link, and that data has been received at the receiver's end with the help of demultiplexer. Demultiplexer demultiplex that data and it transfers that particular signal to the particular destination only. So there are three different types of multiplexing. Frequency division multiplexing, that is FDM. It is an analog technique. Wave division multiplexing, that is WDM. It is also an analog multiplexing technique, and for digital we use time division multiplexing. So as you can see in the diagram, the input line, that is at the server end or sender's end, they have multiplexed the data, and our channel is sending or bifurcated in three different channels. And at the receiver's end we have output lines. There we differentiate this composite signal with the help of demultiplexer. So we have to keep one thing in mind, that is FDM, that is frequency division multiplexing, is an analog multiplexing technique that combines analog signals. As you can see in a diagram, in the diagram 4 we have FDM process. As you can see, there are different composite signals coming from the different channels, and the multiplexer makes or merge these signals. In a simple way you can say that it has been multiplexed by the multiplexer with the help of modulator, and it forms a composite signal which has been traveled through the common communication channel or a link. So FM channel is a best example of this kind of frequency division multiplexing. Then as you can see at the receiver's end, the composite signal has been received by the receiver demultiplexer, and it uses the filter to demultiplex the composite signal, and that signal is demodulated and received by the particular receiver. Now let's assume one example that assumes that a voice channel occupies a bandwidth of 4 kilohertz, and we need to combine 3 voice channels into a link with a bandwidth of 12 kilohertz from 20 to 32 kilohertz. Now show the configuration using the frequency domain and assume there is no guard bands. So what will be the solution? The solution we have that the shift or a modulated, we modulate each of these voice signals or voice channels to a different bandwidth, which is shown in this figure, and then we have to use 20 to 24 kilohertz bandwidth for the first channel, then 24 to 28 kilohertz for second, and 28 to 32 for third channel. So as you can see, we have 3 different lines and we have 3 different bandwidth for the particular channel. So modulator modulates this and combines these frequencies, and these data has been transferred through the common link. As you can see in a diagram here, the data or frequency has been transferred to the common communication channel, and it has been received at the receiver end, and the band pass filter filterized the data, and demodulator sends that demodulated signal to the particular channel. Let's consider one more example that we have 5 channels and each with 100 kilohertz bandwidth are to be multiplexed together. Now we are going to multiplex these 5 channels. What is the minimum bandwidth of the link if there is a need for the guard band of 10 kilohertz between the channels to prevent interfaces? Now here in the first example, guard band is absent. In this example, we have a guard band with a 10 kilohertz capacity. So what will be the solution? As you can see, for 5 channels we need at least 4 guard bands. It will be a gap between the particular frequency. As you can see in the diagram, we have 5 channels having frequency of 100 kilohertz, and we have a gap between 2 frequency, that is 10 kilohertz. So total how many kilohertz frequency or bandwidth we need? We need 540 kilohertz bandwidth. So how we are going to calculate it? It means that we require the bandwidth at least 5 into 100 kilohertz is the minimum bandwidth we have declared for the particular channel, plus 4 into 10, that is 4 guard band into 10 kilohertz, so it is 540 kilohertz. So let's consider it with this example. We have 1 Mbps digital data transmission unit and 60 QAM, and we are transmitting this analog signal through that particular channel, and frequency division multiplex this signal, and it has been transferred to the common link or a common channel with the frequency of 1 megahertz. So as you can see, there are so many or 12 different channels has clubbed together, and FDM combines that data and it transfers data from one node to another or one server to another, and it carries, and at last we have a jumbo group which is nothing but an 16.948 megahertz, and it contains more than 3600 voice channels. So this concept is used for telecommunication for one city, or you can see a mega cities also as well. So the wavelength, now let's discuss about the wavelength division multiplexing. In wavelength division multiplexing, wavelength has been discussed as a count as an lambda. So lambda 1, lambda 2 and lambda 3, these are the three different wavelengths from the three different channels, and they are sharing a common communication link, and the wavelength will be calculated as an lambda 1 plus lambda 2 plus lambda 3, and at the demultiplexer or a receiver's end it has been bifurcated as well. So WDM is another technique which has been used for analog multiplexing, and it has been used to combine optical signal as well. So optical signal, as we know that if we consider an example of a prism at one end, it merge all the rays, that is we have considered three laser signals, that is lambda 1, lambda 2, lambda 3, and this has been merged just like an fiber optic cable carries each and every signal, and at the demultiplexer end, the another prism, that is nothing but a demultiplexer in our case, it differentiate this or the ray which has been coming with from the multiplexer. Now let's discuss about the digital data transmission. For digital data transmission, we have time division multiplexing. In that, as you can see, the channel has been categorized with the different flow or data flow for the particular channel is having a particular time slot, that is 1, 2, 3, 4, and this time slot has been shared with the link as well. So time division multiplexing is a digital multiplexing technique for combining several low rate digital channels into one high rate. So as you can see in a diagram, a synchronized time division multiplexing, what they have combined all the signals from a different channel like A, B and C. Here we have bifurcated the signals which has been coming from this channel, that is A1, A2, A3, B1, B2, B3 and C1, C2, C3, and we have created a frames. A multiplexer creates a frame 1 for A1, B1, C1, frame 2 for A2, B2, C2 and frame 3 for A3, B3 and C3, and that frame has been transferred from the particular channel. So in a synchronous data transmission, there is a link n times faster than the n duration is n times shorter. So let's consider one example that the data rate for each one of the three input connection is 1 kbps if one bit at a time multiplexed. So what will be the duration? And second, each input slot, each output slot, and for each framework we are going to calculate the duration. So let's consider a data rate of each input connection is 1 kbps. This means that the bit duration is 1 upon 1000 s for 1 microsecond, and the duration of the input time is 1 microsecond, and then the duration of each output time slot is 1/3 of the input time slot. So it means that we have the output time slot is 1 upon 3rd microseconds, and for a framework, each framework carries 3 output time slots. So duration for the time slot is, duration for the frame is 3 into 1/3 microsecond, that is nothing but 1 microsecond. So we have to keep one note in the mind that the duration of the frame is same as the duration of the input unit. So as you can see in the diagram, we have a different line A to E, and this has been sent a synchronized signal, and at the diagram B, as you can see, same line A to E, and they have sending a statistical time division multiplexing signal. Okay, that's all for this. Thank you.